All right, welcome back. In the second section on independent and linearly dependent sets, I want to look at the set of functions. So I want to look at independent sets of function and the Wronskian. If you remember from one of the examples where we looked at function, it's quite complicated to determine whether a set of function is dependent or independent. So we have a little trick here. Our goal is to use determinants and derivatives, two really helpful computational tools, to prove that a subset S is linearly independent. All right, let's start right away. Definition 1.4.3, I want to define the Wronskian. I'm going to take f1, f2, and fn be functions that are n minus 1 times differentiable on R. Maybe I need parentheses here, it looks a bit strange. All right, the Wronskian of the function is the function. So I'm going to take a determinant of a matrix. That matrix will depend on X. I'm going to take F1 at X, F2 at X, and Fn at X. That's going to be my first row. Second row, I'll take the same thing, but with the derivative. And I'm going to keep differentiating it. The bottom row will be the n minus first derivative. I really stop at n minus 1 because I want something squared so that I can take the determinant. I want the matrix to be squared, and so I want n rows. So zero derivative is the first row, the nth row would be the nth minus 1. All right, so let's see what that means in an example. Example 1.4.6, I want to compute the Wronskian of the set x, x squared, ex, and 1. All right, so the Wronskian is the determinant of a matrix. First row, I just rewrite the functions as is. Second row, I differentiate it. So the derivative of x is 1, x squared is 2x, e doesn't change, 1 gives me 0, and then I keep differentiating until I get a square matrix. All right, so I want to compute this determinant. Fastest way here, I have a really nice column, so I'm going to expand on that column. Let me look at the signs. I'm going to get minus 1 times the determinant. Let me use these straight lines for determinant. I'm going to get rid of last column, first row, because that's the only non-zero element. And so I'm going to get 1, 2x e to the x, 0, 2 e to the x, 0, 0 e to the x. Now I have an upper triangular matrix. And so I get minus 1 times 2 times e to the x, product of the diagonal entries. You could also expand it, but at this point, this is faster. All right, so the Wronskian in this case is minus 2 e to the x. So it will depend on x, but if I fix a value of x, I get a determinant of a real matrix, and so I get a number. So for every value of x, you get a number, you get a function.